Hi students, this is Mr. Liao. In this lesson, we're going to learn how to solve exponential equations. But first, let's work on the prior knowledge to get some answers for some of the exponent stuff. 1 to the third power, that is the same as 1 times 1 times 1, which is 1. Next, 5 to the third power, that means 5 is multiplying by itself 3 times, which is 125. Next to the fifth power, that is the same as 2 times 2 times 2 times 2 times 2, which is 32. 10 to the fourth power is 10 multiplied by itself for 4 times, so it's 10,000. Next, 1/3 to the fourth power. Typically, when you have that, you can actually give the 4 to the top and the bottom separately. So the same as 1 to the fourth power over 3 to the fourth power. 1 to the fourth power, just a 1. 3 to the fourth power is an 81. And this next one is the same. 1 to the third power over 4 to the third power. So it's going to be 1 over 64. Next, let's review some of the exponential rules that you have learned last year. We have these 5 rules. First one is called product rule, which is when you are multiplying things that actually have the same basis. So it's a multiplication sign in between. The first part, x to the fifth power, is just x times itself 5 times. And the second part is just x times itself twice. And they're connected by another multiplication sign. So altogether, x is multiplying itself 7 times. So it's x to the 7th power. Which means in product rule, if you see them having the same basis, you're actually adding the exponents. Same thing with the next one. 4 plus a -1, that is a 3. So it's actually x to the 3rd power. Next, quotient rule. Quotient rule is the opposite of product rule. Product rule, when you're multiplying, you're adding the exponents. Quotient rule, when you're dividing, you are subtracting the exponents. So it's the same as 5 minus 2, which is x to the 3rd power. Next, x to the 3rd power over x to the 4th power. So in that case, 3 minus 4, so it's in fact x to the -1 power. So that's a quotient rule. The third one is power rule. You see a square on the outside, which means whatever is inside the parentheses is multiplying itself twice. So we have x to the 5th power times another x to the 5th power. So after that, this actually goes back to the product rule, because now it becomes a multiplication that both have the basis. So it's the same as x to the 10th power, because now you can actually add them. But in fact, when you directly deal with power rule, that is 5 times 2, that equals to 10. So that means for this, if you have x to the 3rd power parenthesis with 4 on the outside, is actually 3 times 4. So it's the same as x to the 12th power. Before we talk about negative exponents, let's talk about the 0 exponent first. Anything to the 0 power is, in fact, just a 1. As for the reason, because x to the 0 power is the same as, say, x to the 1 minus, or let's say 2 minus 2, because 2 minus 2 is a 0. And if it's subtraction, you're actually dealing with quotient rule. So it's x squared over x squared. So anything divided by itself, well, it's a 1. So that's why anything to the 0 power is a 1. Negative exponent, we're going to rewrite it the same way as the 0 exponent. So that is the same as a 0 minus 2. So when it's 0 minus 2, it's the same as x to the 0 power over x squared. And we have just talked about x to the 0 power is 1. So it's in fact 1 over x squared. So in other words, whenever you see negative exponents, you're just rewriting it, flipping the fraction, get rid of the negative sign. So technically right now it's on the bottom of it's on the top of the fraction. So you flip it to the bottom of the fraction and then get rid of the negative sign. So same thing here. It's actually currently over 1. So we're going to flip it to the bottom of the fraction, but get rid of the negative sign. And that will give us 1 over 49. If you are wondering, wait, but what if it's already on the bottom of the fraction? Let's say you have x to the -3 power. 1 over x to the -3 power. It's already on the bottom of the fraction, so we're going to flip it to the top, but also get rid of the negative exponent. So it's actually x cubed over 1, which is x cubed. These are all the exponential rules you have learned before. Solving exponential equations. Now we're going to use these exponential rules to solve equations. We have actually learned equality property of exponentials in Unit 2, which is, as long as the bases are equal, then the exponents must also be equal. And based on that rule, here's how we're going to solve exponential equations. We need to make sure the bases are the same on both sides of the equation first. So we're going to use all the rules, and we have to make sure the bases are the same, and then we can just get rid of the bases, or in other words, ignore the bases, set the exponent equal to each other to solve the equations. We actually learned some simple exponential equations to solve in Unit 2. I'll link that video in the bottom right corner right here. Now let's get into the examples. Example 1. The bases are already the same that we have checked, so we can ignore them. The exponents has to be equal, so x plus 2 equals 2, x equals 0. Example 2. The bases are already the same, so we can just use the exponents. Negative n minus 1 is 3n plus 1 minus 3n on both sides, add 1 on both sides. So we're going to have negative 4n, that equals 2. A 2, divide both sides by a negative 4. We have n equals negative 1/2. That's example 2. Example 3, 125 on the right side. That's not the same base as the 5. But because the 5 couldn't be simplified anymore, well, it has to be base 5. So you're going to need to figure out how to rewrite 125 as 5 to a certain power. You have two options. One, you can actually type in your calculator 5 to the x power, and then use second, and then graph to actually get the table. Then you can actually look for which one gives you 125. The other way is you can use your calculator to just try 5 to the first power, 5 to the second power, 5 to the third power, and keep trying until you actually see 125. In this case, 125 is 5 to the third power. The bases are the same, so the exponent has to be equal to each other, which is negative 2r, that equals to 3. And finish solving, divide both sides by negative 2. R is negative 3/2. That is example 3. Moving on, example 4. So you see the left side is an 8 to a certain power, so you might be like, oh, I need to rewrite 128 into 8 to a certain power. Then you start trying your calculator, you will realize 8 to the second power is 64, 8 to the third power is 512. So you can't exactly write it as 128. That tells you you have to change both sides so that they are going to give you the same number. So 8 could actually be written as 2 to the third power. That means you're going to need to try to figure out what is 128 if you try to rewrite it as 2 to a certain power. If you type in your calculator, either getting the table or just keep trying, you're going to notice 2 to the 7th power is 128. As for the left side, we're not fully done because we only rewrote the 8 as 2 to the third power. But we still have the m on top of 8. So in fact, we need parentheses, and we still have the m outside. The reason is the m is actually on 8. If you only put the m without the parentheses, that actually might mean the m is just on the 3. So we actually need to make sure, even though we rewrite the 8, the whole thing is actually having an m as the exponent. So this means you have parentheses, and you have a variable on the, you have a exponent on the outside, so you need to multiply them together. This is the same as 2 to the 3m, which equals 2 to the 7th power. The same basis, so 3m equals 7, m is 7/3. Example 5, we have subtraction sign in between, so we can't actually deal with it yet until we only have multiplication or division. So 10 to the 3x minus 4, we're going to need to add 100 on both sides. The right side is going to become 10,000. And 10,000, well, the left side is a 10. 10 could not be rewritten as anything to a certain power. So 10 is the lowest we can go, which means we're going to rewrite the right side using a base 10. 10,000 is in fact 10 to the 4th power. Now they're the same base. 3x minus 4 equals 4. 3x equals 8. So x is 8/3. That is example 5. Example 6, you may notice everything is already base 3, but the left side has a multiplication sign. So we're going to need to use product rule to combine the exponents. Product rule means we're adding the exponents, so it's negative 2b plus a negative b on the left side. The right side is 3b minus 3. Let's simplify the right side. It's 3 to the negative 3b power equals 3 to the 3b minus 3 power. The bases are the same, so negative 3b equals 3b minus 3. Subtract that to the left side. We have negative 6b, that equals to negative 3, divide both sides by negative 6. b is 1/2. That is example 6. Moving on, example 7. Left side already have base 2, and that can't go any lower. Tells you you have to rewrite 16 using a base 2. 16 is 2 to the 4th power. The left side, we actually have product rule, so we're going to need to combine the exponents. 2n plus negative n plus 1. That equals 2. 2 to the 4th power. Same base, so that means the exponents have to equal to each other. The top on the left side is 2n minus n, which is an n plus 1. The right side is just a 4. So n equals 3. Next, example 8. Left side already has a 3 that tells you, well, and 3 can't go any lower. That means for this question, you're going to have to change everything into a base 3. So we're going to keep the first part. The 27 could be rewritten as 3 to the 3rd power, still with having a multiplication sign in between them. The right side, 1, you still need to rewrite it as a 3 base something. Well, 1 is, well, for anything to rewrite as 1 is a 3 to the 0 power. So whenever you get a question that has a 1 as a number and you actually need to rewrite it as an exponent, you just look for what base it needs to be, and it's going to be the 2 to the 0 power. Left side has a multiplication symbol, so we need to add the exponents. Negative 2n plus 1 plus 3. The right side is just 3 to the 0 power. So that means the bases are the same. Negative 2n plus 4 equals 0. So negative 2n equals negative 4. And equals, divide both sides by negative 2, a 2. That is example 8. Example 9. Left side has a base 3. Right side also has a base 3. And 3 can't go simpler. That means we're just using them. The right side has parentheses with an exponent on the outside. So we do need to use product rule to simplify that. That is going to be 3 to the 35th power. We're multiplying the exponents. The left side is 3 to the 4p minus 1. Same base. So 4p minus 1 equals 35. 4p equals 36. So p equals 9. That is example 9. Example 10. The numbers we have as bases are 3, a 27, and a 9. Clearly, the simplest is a 3, so we're going to need to rewrite everything using a base 3. Copy down the first part. Still multiplying the second part. First, we're going to need to rewrite that 27, which is 3 to the 3rd power. But don't forget, you still have the exponent outside the parentheses, so the p plus 1 outside the parentheses. The right side is going to be a bit more complicated because we already have 2 exponents. Let's actually simplify that first. 9 to the 5th power with a 2 on the outside is actually 9 to the 10th power. And then we're going to rewrite that 9 into 3 squared, but still having the 10 outside the parentheses. Next, we have a bunch of parentheses, so we need to deal with them using the product rule. So 3 to the 4p minus 1 times, well, this is actually a 3 times p plus 1 together. So it's actually 3 times p, then 3 times 1. So that will become 3p plus 3. Right side, 2 and 10 even multiplied together, so it's 3 to the 20th power. Still not done because the left side we have these multiplication symbols, and they're the same bases, so you actually need to add the exponents. So that is 3 to the 4p minus 1 plus 3p plus 3. Right side is 3 to the 20th power. Left side, we can add the exponents together. They are the same base and just one thing on each side now. So 4p plus 3p is 7p. Negative 1 plus 3 is plus 2. That equals to 20. So 7p equals 18, and p equals 18 over 7. That is example 10. Now the last 3 examples. Example 11. So this time we're dealing with the fractions. Left side has a base 7, and 7 can't go any lower, which means we have to rewrite the right side using 7. I'm not going to deal with the fractions yet. The first step, I'm just going to rewrite this number that I see, 49. That is the same as 7 squared. Now I'm trying to get rid of the fractions so that they are the same base. Right now, even though you're like, oh yeah, they both are 7, but on the right side, the 7 squared is actually on the bottom of the fraction. In order to take it out of the fraction, I need to give it back the negative exponents. So that is 7 to the negative 2 power. Now they're the same base, so 2x equals negative 2, x equals negative 1. Example 12. First, let's deal with this question. The right side has a base of 4, even though that could go lower. But let's check the 16. Well, 16 could actually be rewritten as a base 4. So I'm going to keep the base 4 on the right side. As for the left side, it's a 16, and I need to rewrite it using base 4. So that is 1 over 4 squared. Since I need to take it out of the fraction, I need to give it back to the negative exponents. So it's 4 to the negative 2 power. Same base, so negative 2 equals 5x minus 7. Add a 7 over. So we have 5 equals 5x, which means x equals 1. Now I'm going to change this question a little bit. Let's say you actually have a different question. Slightly different. 1 over 16. 1 over 16. That equals to 8 to the 5x minus 7. So let's say we're dealing with this question, slightly different. Now you may realize, well, 16 can't be rewritten using a base 8. Some of you might be like, wait, 16 is 8 times 2. Well, that's multiplication, is not exponents. So you can't write it using a base 8, which means you have to change the 16 and 8 into something else that they both could be rewritten as. That will be 2. So let's deal with the left side first. That will become the same as 1 over 2 to the 4th power. Since I need to take it out of the fraction, I need to give back the negative exponent. So it's going to be 2 to the negative 4 power. As for the right side, well, I need to rewrite that 8 using the base 2. That is 2 to the 3rd power. But that's just rewriting the 8. The 5x minus 7 is still going to be another exponent. So parentheses, the 5x minus 7. So let's simplify it. The 3 again is actually being multiplied with the whole thing of 5x minus 7. So in fact, that's distribution. 2 to the 3 times 5x is 15x. 3 times negative 7 is a minus 21. Now they are the same base. So negative 4 equals 15x minus 21. Add the 21 over. 17 equals 15x. So x equals 17 over 15. So this is the one where one number can't be rewritten as another, then you have to rewrite both numbers using something else. Example 13, the right side is the base 2. Well, that means I can try to get 64 into a base 2, well, which is 2 to the 6th power. Still having the 2x plus 3 on the outside the parentheses. The right side is just 2 to the 5x minus 7 power. Hey, now I need to rewrite that fraction, changing into a normal base 2. That would be 2 to the negative 6th power, still having the 2x plus 3 on the outside. And it's 2 to the 5x minus 7 power. Again, whenever you deal with product rule, it's multiplying between the exponents. And that means you actually sometimes have distribution to do like this. Negative 6 times 2x, and then negative 6 times 3. So it's negative 12x to minus 18. That equals 2 to the 5x minus 7 power. Same base, so the exponents have to be equal to each other. Negative 12x minus 18, that equals to 5x minus 7. Subtract 5x over, add 18 on both sides. We have negative 17x equals 11. So x equals negative 11 over 17. That is example 13, and that is everything for the solving exponential equation lesson. Thank you.